All right, welcome back to another lecture. In this lecture, we're going to talk about how to perform inference on multiple proportions. In the past, we've talked about how to perform inference on a single proportion or on a single mean through one sample hypothesis testing and by constructing confidence intervals. Here, we're going to just focus our attention on proportions, and we're going to talk about what if you want to compare two proportions or three proportions or more? How would we do that? So that's what we're going to talk about. And we'll introduce three tests for doing this. So three different hypothesis tests. We'll have the two sample proportion test, the goodness of fit test, and the homogeneity of proportions test. Now, this first test, the two sample proportion test, it follows the p-value for that test is computed using the normal distribution, which we're already familiar with. These two tests, though, the goodness of fit test and the homogeneity of proportions test, the p-values for those are computed using the chi-square distribution, which we have not talked about yet. Now, I'm not going to really take a lot of time to introduce you to the chi-square distribution because we won't be using that distribution directly to do the computations of the p-values. We're just going to use an app like we have before. I only mention that they follow a chi-square distribution because these tests are sometimes called chi-square tests, and I wanted you to understand why. By the way, this is the Greek letter chi, okay? And it's pronounced chi, right? It rhymes with sky. It's not pronounced chi, even though it's kind of spelled like it seems like it should be pronounced chi, but it's not. It's not chi. It's chi. Anyway, that's not that's not a major issue, but so let's get into it now. Fair warning. This is going to be a longer section. I think most of the sections until the end of the course are going to tend to be a little bit longer than the sections that we saw in the first two units. But we'll be covering fewer sections per week in the course. So it'll amount to about the same amount of work. Anyway, let's get into it. Let's talk about these three tests. So starting with the two sample proportion test. So first of all, just notationally, because in a two sample proportion test, we're going to be comparing two groups, we need to use subscripts to differentiate between the groups, right? So we'll use subscripts of 1 to represent the first group and subscripts of 2 to represent the second group. But otherwise, these symbols all mean the same thing as they have before, right? So P1 is the population proportion of group 1, right? And N1 is the sample size of group 1, and so forth. N2 would be the sample size of group 2, and so on and so forth. Okay, this is what a two sample proportion test looks like. And by the way, I'm not going to give you the reasoning behind how the apps that we use are computing these p-values for us, but I will provide you links so that if you're curious and interested to know, you can look it up. But okay, so let's go through the hypothesis testing steps for a two sample proportion test. Now, these are going to be the same steps as usual, but there are going to be some subtle differences. For example, notice the way that the null and alternative hypotheses are stated here. Instead of it being the null hypothesis being that p equals some number, right, like 0.3 or something, and then the alternative being that p does not equal that number. Here we just have p1 equals p2 and p1 not equal to p2. So we won't actually be replacing these symbols with any numbers. Okay, they'll just be the null hypothesis is that the samples have the same population proportion, right? The two groups have the same population proportion. And similarly for a left-tailed or a right-tailed test, okay? So in that regard, I think that it's actually kind of easier. I think that two sample proportion tests are a little bit easier than one sample proportion tests. Step 2, of course, is to gather the sample evidence. And in this case, we'll have two sample proportions that we're trying to compare, so we'll have to compute two of those. And then finally, we'll compute the p-value. Now, we're going to use an app from artofstat.com. Okay, specifically, we're going to follow this link right here. But you could also navigate there from artofstat.com, which actually I think is what I'm going to do in this lecture. So I'm just going to go to artofstat.com throughout this lecture, and then I'm going to navigate to the web app that I want. So if I want to compare two proportions, then I'm going to go to the compare two proportions web app. Okay, and again, I'm not going to go into any detail about how the web app is computing this p-value, but if you want to know, you can follow this link right here. Once we have our p-value, we can use it to make a decision, and we do this the same way as usual, right? If our p-value is less than alpha, then we reject the null hypothesis. If our p-value is not less than alpha, then we do not reject the null hypothesis. And by the way, even though I'm not going into detail about how the p-value is computed, let me just say the meaning of the p-value is the same in this for these tests as it has been for all of the tests that we've run in the past. Namely, the p-value is the probability of obtaining the sample results that we obtained if we assume that the null hypothesis is true. In this case, the p-value would be the probability of obtaining these sample proportions if we assume that the population proportions are the same. Okay? If the likelihood of obtaining these sample proportions is really small when we assume that the null hypothesis is true, then that tells us we probably shouldn't assume that the null hypothesis is true, and so we reject the null. That's why we reject the null hypothesis when we have a small p-value. Once we've made our decision to reject or not reject the null, then we can write a conclusion, which is about what our decision means for the alternative hypothesis. If we've rejected the null, that means there's evidence in favor of the alternative. If we do not reject the null, then that means there's not sufficient evidence to support the alternative, right? One last thing to say before we look at some examples. We have to check conditions technically before we run any hypothesis. Well, before we run any parametric hypothesis tests like the ones that I've introduced so far, there are conditions that we're going to have to check. This has not been a major emphasis of our course, and it's going to continue to not be a huge emphasis for me. But just know that in the real world or whatever, you would have to check these conditions to make sure that the results of the test are actually valid, okay? So in this case, the conditions are the samples have to be independently obtained. We'll talk a little bit more about what that means in the next section. The sample sizes have to be no more than 5% of the population sizes. This is really a check for independence, okay? So each of our sample sizes has to be less than 5% of its population size. That's a difficult condition to check because most of the time the population size is not given to you. But you could do some educated guessing and kind of figure that out. Again, this is not going to be a heavy emphasis in this course. And then finally, we have to make sure that we are actually authorized to use the normal distribution to compute the p-value, and this is the check to do that, right? Each of our sample, it has to be the case that n times p times q is bigger than or equal to 10 for both of our samples, for group 1 and group 2. If any of those conditions fail, then the results of this test are not valid, okay? But most of the time the conditions are going to hold, and I'm not really going to ask you to check the conditions for the most part. So let's take a look at an example. This first one says, Johns Hopkins researchers conducted a study of pregnant IBM employees. Among the 60 employees who worked with glycol ethers, 20 had miscarriages. But among 750 who were not exposed to glycol ethers, 120 had miscarriages. Okay, so you could look up what glycol ethers are. I'm not even sure if I'm saying that right, to be honest with you, but I do know that glycol ethers are found in certain cleaning supplies and in certain cosmetic supplies and things like that. So, among 60 employees who were exposed to these things, 20 had miscarriages, which seems like a pretty high miscarriage rate to me. But the question is, is that higher than the miscarriage rate among people who are not exposed, right? Because if it's not, then we don't really have any reason to be concerned. But if it is, well, then we might want to be careful to avoid glycol ethers, especially if you're a pregnant woman, right? Anyway, that's what part A asks us to do. It says at the 0.01 level of significance, test the claim that the miscarriage rate is greater for women exposed to glycol ethers. So we're going to follow the same steps of our hypothesis testing procedure as usual. Okay, the null hypothesis is that no, there's no difference in these proportions. P1 equals P2. Maybe there's a difference in the sample proportions, but that is just due to random chance and it's not reflected in the populations, right? So the null hypothesis is that the population proportions are equal. The alternative hypothesis is that the miscarriage rate is greater for women exposed to glycol ethers. Now here we need to be careful. It doesn't matter which group we label group 1 and which group we label group 2 as long as we remain consistent throughout the problem. So in my case, I'm going to say that the group of women who were exposed to glycol ethers is group 1 because they were the first group mentioned. And then the women who are not exposed, I'm going to call that group 2. So if the miscarriage rate is greater for women exposed to glycol ethers, right, that would be group 1. So the alternative hypothesis is that P1 is greater than P2. So that's step 1 of the procedure. Now, step 2, we can collect some sample evidence. We can say, well, what were the sample proportions in question here, right? For group 1, the sample proportion was 20 out of 60. Okay, that's 0.333 repeating on forever. So 33.3% of the women in that group had a miscarriage, which is really sad. In group 2, the sample proportion was 120 out of 750, which is exactly 16%. So right off the bat, before I even run this test, I'm noticing that the sample proportion of miscarriages among women exposed to glycol ethers is twice as large as the sample proportion of miscarriages among women not exposed. And to me, that kind of is a red flag, right? I suspect that we're going to end up rejecting the null hypothesis here. But the only way to know for sure if that's what we end up doing is to go ahead and run the test. And so we should compute the p-value. That's step 3. To compute the p-value, I'm going to go to art of stat. So let's just head over to art of stat so that we know what kinds of things we're prompted for, so that we know what kind of work we need to show and all of that. So let's head over to artofstat.com, and I've already got it open in my browser, okay? So if you go to artofstat.com and then you click on, so when you go there, it'll open up to this homepage. But if you click on web apps at the top of your screen, then you can scroll down until you find, we're looking for, so here it says confidence intervals and tests comparing two groups. This is exactly what we want. In our case, we're trying to compare two proportions. So I'm going to click on this tool right here. You could always just follow that link directly also. Okay, and they have, as always, examples from the textbook that they're using. We want to use our own example, so we'll click on number of successes. And it looks like what we're being prompted to enter is the sample size and the number of successes for each group. And then I would imagine also we're going to want to do a significance test rather than a confidence interval. And so we have to enter what the alternative hypothesis is, whether it's left-tailed, right-tailed, or two-tailed, right? Okay, but let's fill this stuff in. So for group 1, our sample size was 60. There were 60 women, and 20 of them had miscarriages in group 1. In group 2, the sample size was 750, and there were 120 miscarriages in that group. So you can see they give you a nice little bar chart over here so you can compare the groups visually. You can also see the sample proportions that we computed a second ago right here. You have your test statistic right here in case, you know, in the homework you're prompted to enter the test statistic. You can see it here or here, right? And then, of course, the p-value is what we're really here for. Let's be careful, though, because I think this is running a two-tailed test. From the picture, it looks like it's running a two-tailed test. We don't want it two-tailed. We want it to run a right-tailed test. Okay, so here's our p-value, 0.0003. So let's write down the results of that. So we went to artofstat.com. We entered for the sample size for group 1, we put in 60, and for the number of miscarriages, we put in 20. For group 2, it was 750 and 120. And then the p-value that we got was 0.0003. Okay. So step 4 is to make our decision. Our significance level is 0.01, and this is far less than that, right? So we would say 0.0003 is less than 0.01, so we reject the null hypothesis, right? In other words, well, actually, part B is going to ask us to interpret this p-value anyway, so I was about to do that, but we'll do that in a second. But yeah, we're going to reject the null hypothesis here. We got a small p-value. We're rejecting the null in favor of the alternative, okay? So in conclusion, we would say there is sufficient evidence to conclude that, and if you haven't caught on to this already, most of the time you can copy and paste from the question. Like in this case, we were asked to test the claim that the miscarriage rate is greater. Okay, so we can just copy and paste that. We can say there's sufficient evidence to conclude that the miscarriage rate is greater for women exposed to glycoethers. Okay, so just as we suspected, right? Okay, so part B asks us to interpret this p-value. Well, as always, the p-value is the probability of obtaining the sample statistics that we obtained if we assume the null hypothesis to be true. In this case, the null hypothesis was that p1 equals p2. So operating under the assumption that the populations have the same proportion, there is only about a 0.03% chance of obtaining the sample proportions that we obtained. That's a very small probability, okay? It's so small that it makes us doubt our assumption, right? It makes us think, well, maybe we shouldn't assume that the null hypothesis is true, and so we reject it, right? So what does the p-value mean? We would say, if we assume that p1 equals p2, right? If we assume that the null hypothesis is true, then there is only a 0.03% chance of obtaining two samples as different or maybe I should say two sample proportions as different as the ones we obtained. You could say as different or as far apart or something like that. Okay. And this is why we reject the null hypothesis in this case. Now, in the past, I've had students who have been really kind of bothered with this reasoning because they think, well, instead of us being suspicious of the null hypothesis, shouldn't we be suspicious of our sample proportions instead? Like maybe there was something wrong with the samples. And that is a possibility, okay? That's a possibility. But it's a very slim possibility. That's exactly what the p-value is measuring, right? It's a very slim possibility. So it is possible that that's what's going on here, but it's very unlikely. Assuming that good sampling methods were used, right? It's very unlikely that we're getting proportions that are so distinct. Now, maybe good sampling techniques were not used, okay? And that's where you would have to look at the methodology in the study, right? And really, that's kind of hard work, but you have to look at the methodology of the study and see, like, wait a second, did the researchers do something strange here? But assuming that they did their work honestly, then the likelihood that we would have gotten these sample proportions by random chance is very, very slim. So the only assumption we made was that the null hypothesis was true, and the likelihood here is so small that we just it casts doubt on the null hypothesis, so we reject it. Okay, part C says construct a 99% confidence interval for the difference in miscarriage rate between those exposed and not exposed to glycol ethers. Comment on the practical significance of being exposed to glycol ethers during pregnancy. Should pregnant women be wary of glycol ethers? Well, yeah, what we've already found is that there's a statistically significant difference in the miscarriage rate of women exposed versus women not exposed. But the question is, how severe are the consequences, right? And so we want to look at a confidence interval for that. So going back to this app, and they might make us, they're going to make us re-enter all of the stuff. That's okay. We can do it real quick. So in sample 1, we had sample size 60, 20 successes. In group 2, it was 750 observations and 120 successes or miscarriages. Okay, and they wanted a 99% confidence interval. So I'm going to slide this over to 99%. And there we go. So the confidence interval for the difference is somewhere between 0.01, if we rounded to 3 decimal places, we could say between 0.013 and 0.334. Okay, so 0.013 and 0.334. So again, we got this from Art of Stat. And the confidence interval, the 99% confidence interval that we got was 0.013 approximately to 0.334, I think it was. 0.0. Yep. Yeah, that's right. Okay, but we went to Art of Stat. We put in the same stuff that we had before, right? X1 was 20, N1 was 60, X2 was 120, and N2 was 750. Okay, and this is the confidence interval that we're getting. Something that I'll point out to you is that that's a very wide interval. Man, that's a wide interval. We're saying that somewhere between 1.3%, there's somewhere between a 1.3% and a 33.4% difference. So how significant is the difference in miscarriage rate? Well, potentially it's not that significant, right? Or it could be devastatingly significant, right? This interval is just very wide. So to comment on the practical significance, we could say, well, the increase in miscarriage rate is somewhere between 1.3% and 33.4%. On the lower end, that's not much of a practical difference. But on the upper end, it's devastating. I would say more data are needed, which kind of leads to part D. It says, what do you think is the cause of the confidence interval being so wide? And I think it's small sample sizes. I think that's the issue here. This sample size for group 2 is a good sample size, right? 750, that's a good sample size. But this sample size for group 1 is a little on the small side, and I think that's why we're not getting very specific results from our confidence interval. So a small sample size for group 1. Right, that's what's causing the confidence interval to be so wide. If we want to get a more, precise measurement for the increase in miscarriage rate, we're going to need some more data, okay? All right, so that is that first example. Now, I know that I say this from time to time, so I might sound a little bit like a broken record, but you should really pause the video and try this out on your own. I'm going to just go ahead and forge through and continue working out these examples, but as we encounter new examples, I think it's a really good idea for you to pause and try things out on your own. So pause the video here, try this one out, see how you do, and I'm going to go ahead and give you my solution. So it says, in clinical trials of Nasonex, 3,684 adult and adolescent allergy patients were randomly divided into two groups. The patients in group 1, the experimental group, received 200 micrograms of Nasonex, while the patients in group 2, the control group, received a placebo. Of the I've got some typos here. No, that's not a typo. Okay, of the 2013 patients in the experimental group, I was getting confused because this is like overall the number of people, but this number is just describing the people in the experimental group. Okay, 547 reported headaches as a side effect, and of the 671 patients in the control group, 427 reported headache as a side effect. Is there evidence to conclude that the proportion of Nasonex users that experienced headaches as a side effect is greater than the proportion in the control group? Well, the null hypothesis is going to be that there's no difference. The alternative hypothesis is going to be that P1 is greater than P2. So it looks like another right-tailed test. We want to know if the patients in the experimental group, that's group 1, have a greater proportion of headaches than the people in the control group 2. So let's see what the sample evidence has to say. In group 1, 547 out of 2,013 patients experienced a headache. 547 out of 2013. So you can punch that into your calculator. That's approximately 0.271, or sorry, 0.272. So about 27%, okay, of people in the experimental group. In the control group, it was 427 out of 1671. 1671. And that comes out to about 0.256, so about 26%. Looking at those proportions, I would say there doesn't seem to be much of a difference here, okay? But we've got to run the test to see. My intuition has been off before, so the only way to know for sure is to run the test. So we got to get the p-value. We're going to go to art of stat. For the number of observations in group 1, we're going to put in 2013. And for the number of successes, 547. In group 2, it's 1671 observations and 427 successes. And let's see what we get for our p-value. Okay, so group 1, we have 2013 and 547. And in group 2, we have 1671 and 427. And I'm not looking for a confidence interval just yet. I want to run a hypothesis test, and we wanted it to be right-tailed. Okay, so our p-value is 0.1335 approximately. All right. That p-value is too large for us to reject the null hypothesis, right? It's not less than 0.05, which was our level of significance in this case. So do not reject H null. Okay, in other words, if we assume that the population proportions are equal, then there's about a 13% chance that we would have obtained sample proportions that are as different as these two sample proportions are. Well, 13% is not that unusual, and so it gives us no reason to doubt the null hypothesis. We have no reason to doubt the assumption we made, so we're not going to reject it. And that means there's really not sufficient evidence to support the alternative. Okay? And again, you can probably just copy and paste. There's not sufficient evidence to conclude that the proportion of Nasonex users who experienced headaches as a side effect is greater than the proportion in the control group, right? You could copy and paste that. Or if you can find a faster way to say it, that's fine. But there's not sufficient evidence to conclude that the proportion of Nasonex users with headaches is greater than that of the control group. Okay, follow-up question. Part B, is the result of this hypothesis test good news or bad news for Nasonex? Well, that's a good question, right? What we were testing is whether the proportion of Nasonex users who experienced headaches as a side effect was greater than the proportion in the control group. If we had found that the proportion of Nasonex users was greater, right, if we had rejected the null hypothesis, that definitely would have been bad news for Nasonex, because what that means is that their medication probably causes headaches, right? And then, either they're not going to receive FDA approval, or it's just not going to sell as well as potentially other medications that do the same thing, because it has this nasty side effect, right? But it seems that that's not really the case. We didn't reject the null hypothesis, which doesn't exactly mean that the proportions are the same, but loosely speaking, we could say, well, we don't have enough evidence to say that the proportions are different, right? So this is good news for Nasonex. It means that they weren't convicted, right? They sort of won their day in court, I guess you could say. So this is good news. This is good news because if we had rejected H null, then that would mean that Nasonex likely causes headaches, right? But we didn't reject the null. So that's good news for them. Okay, part C says to construct and interpret a 95% confidence interval for the difference in the proportions. Let's see. A 95% confidence interval. I'm going to have to redo this every time, aren't I? Okay, so it was 2013. 547. 1671 and 427. Oh, confidence interval is what we want here. We want a 95% confidence interval, in fact. Notice that this confidence interval, interestingly, goes all the way to negative 0.1. So it goes below 0. So let's write that down and talk about what that means, okay? So our confidence interval is somewhere between, we would say, negative 0.012 and 0.045. So we went to Art of Stat. And we entered our statistics. I'm just going to cut to the chase and write down the confidence interval. It was 0.012. Oh, sorry, negative. Negative 0.012 to 0.045. The difference in the proportions is somewhere between negative 1.2% and 4.5%. Now, obviously, this answer right here doesn't make a lot of sense. Negative 1.2%, what does that even mean? Really, we would just say like 0%, somewhere between 0% and 4.5% difference, which corresponds nicely to the results of our hypothesis test, right? Because what we're saying is that, well, it's possible that there isn't a difference at all, right? It's possible that the difference is 0%, which is why we did not reject the null hypothesis when we ran the hypothesis test. Okay, Part D says, note how narrow the confidence interval is in this case compared to example 1. Yeah, I mean, in example 1, just to take a look back at that, there was like a 32% gap. the width of the interval was like 32%. Here, the width of the interval is only like 5 or 6%. So it's significantly more narrow, and I think the reason for this is because of sample sizes, right? Our sample sizes were both large, so we were able to make a pretty accurate prediction, okay? Our sample sizes are both large. So we're able to make good predictions with that. It's just that these particular predictions don't really show much of a difference. So Nasonex is vindicated. Okay, so that's it for the two-sample proportion testing. Let's look at goodness of fit testing. So the goodness of fit test is used to determine whether the sample proportions in the data that we've collected match with some hypothesized distribution. For example, suppose we want to test whether bags of M&Ms contain 13% brown, 14% yellow, etc. candies, right? In the goodness of fit test, the way that we would state our hypotheses here is we would say P1 is 13%, P2 is 14%, P3 is 13%, okay? And hopefully you see where I'm getting these numbers, right? P1 right here, P2, P3, right? P4 is 20%, P5 is 24%, and P6 is 16%. The alternative hypothesis is going to be that the null hypothesis is not true, basically. And there are lots of ways that the null hypothesis could fail to be true, right? It could be the case that P1 and P3 are different, but the other 4 proportions are all the same. Or maybe all of the proportions are wrong. Or, maybe 3 of them are wrong. Maybe P5 and P6 are wrong, but the rest of them are good. So there are all kinds of ways. So instead of trying to write down all of the ways that the null hypothesis might fail to be true, we're just going to write out in words that at least one proportion, and I'm going to abbreviate that by calling it P sub I, at least one proportion is different than stated in the null hypothesis. Okay, so that's how we set up the hypotheses. Now we test the null hypothesis here by determining how well the collected data fits with the distribution posed in the null hypothesis, and that's why it's called a goodness of fit test. Some notation to get us started here. Little n will be the sample size as usual. P sub I is the proportion of individuals with characteristic I. E sub I is the number of individuals who are expected to have characteristic I. Note that E sub I should be our sample size times the proportion of people with characteristic I. So n times P, right? Or n times Pi. O sub I is the number of individuals observed to have characteristic I. And those values are not computed, they're obtained from the data, okay? And then finally, K is the number of different proportions being tested. In the M&M's example, we had 6 proportions that we were testing, so K equals 6. Okay, so with all of that in mind, here are the steps for a goodness of fit test. We're going to state our null and alternative hypotheses as usual. And then step 2 here, I'm going to leave this as an optional step. But, if we were to collect our sample information, this is what it would be, right? We would want to compute the sample proportion of each group. And that's just going to get to be really tedious. Fortunately, when we go to run this test in the app, it will do a lot of that work for us, although it might not give us the sample proportions. We can play around with it and see if we can get it to give us sample proportions, but it will definitely give us expected values and observed values. And we can kind of base some of our reasoning off of comparing those things, the expected values and the observed values. I will show you how to compute the p-value when we go over to the app and when we take a look at an example. And if you want an understanding of how the app is computing the p-value, you can watch or you can follow this link right here and read that on your own. But the p-value is going to have the same meaning as usual, right? It's the probability of obtaining the sample statistics that we obtained if we assume the null hypothesis to be true. If that probability is really unlikely, really small, then it gives us reason to suspect that the null hypothesis is not true, and so we reject it. So small p-value means reject the null hypothesis. Okay, conditions to check here. All of our expected values have to be more than 1. And at least 80% of our expected values need to be more than 5. Okay, so they all have to be more than 1, and at least 80% of them need to be more than 5. Now, if our sample size is large, then those conditions are pretty much going to be met. Okay, so again, not going to spend a ton of time checking conditions, but in case you encounter that in the homework or something, those are the conditions to check for this test. So let's take a look. Example 3 here says Mars Inc. claims that there are 13% brown, 14% yellow, etc. Right? This should look familiar, I think. Candies in every bag of M&Ms. We randomly select a bag of M&Ms, and we counted the number of M&Ms that were each color, and we obtained these results here. At the 0.05 level of significance, can we conclude that the bag that we purchased agrees with the manufacturer's claim? Well, that is the null hypothesis in a goodness of fit test, right? That the proportions match, right? That P1 equals 13%, P2 equals 14%, and so forth. We've been through this already. The alternative is that at least one proportion is different than stated. Step 2, I'm going to leave that up to the computer to do for us, okay? So we'll kind of move on to step 3 and get our p-value. We're going to go to art of stat, and I'll show you what we need to do in this case. So let's head over to art of stat. I'm going to need a different app here. So we don't want to compare two proportions in this case. We want to keep scrolling down, and we're going to open up this chi-square test. So remember, the goodness of fit, the p-value for the goodness of fit is calculated with the chi-square distribution. So we're going to use a chi-square test. We'll open this guy up. And up here in the top menu, you have your choice of either a homogeneity test or a goodness of fit test. We're going to talk about the homogeneity test in a second. Let's click on goodness of fit test, since that's what we want to run. And we're not going to use an example from their textbook. We're going to use a contingency table. And here we have to do a little bit of work just typing in the different categories. First of all, we should tell this calculator how many categories we have. We're comparing 6 M&M colors, so we have 6 categories, right? And then we can write down what those colors are. They were brown, brown, yellow, red, orange, blue, and green. Okay, Now, in this row where it says counts, this is where we're going to put our observed counts, right? This would come from the table in the notes, right? It comes from this table that I circled. So we're going to enter those numbers for our counts. So for brown candies, there were 17. Why does it do that? 17. For yellow candies, there were 20. For red candies, there were 7. Orange, there were 9. Blue, there were 13. And green, there were 6. For props, right? That props is their abbreviation for proportion. This is where we're going to put our null hypothesis, basically. Okay, so the null hypothesis was that there were going to be 13% brown candies, 14% yellow, 13% red, 20% orange, 24% blue, and 16% green. So once you have all of those things in there, then you can click this little blue button that says submit. And you get all kinds of good stuff from this. We're given the p-value, which is what we're here for. You're also given the test statistic in case you're asked for the test statistic. This is it. You're also given a chart here that has not only the observed counts and the hypothesized proportions that we entered, but it also has the expected counts. You could use this row, this expected counts row, to check your conditions. Remember, the conditions were that all of the expected counts need to be more than 1, which they are, and at least 80% of them need to be more than 5. Well, they're all more than 5 in this case, so the conditions hold. You're also given a row here called residuals. The residuals, well, okay, we're going to talk about this in a second. So, but the residuals, maybe let's just talk about it now since we're on this page. The residuals tell us the difference between what we observed and what we expected, right? So if these proportions that were hypothesized were correct, then we would have expected to find about 10 yellow candies in the bag. But what we actually found were 20 yellow candies in the bag, and that's a difference of about 10, right? So that's what this residual is measuring. 20 minus 10.08 or whatever this was. They've rounded some of these values, but that's the idea. And 7 minus 9.4 is negative 2.36 and so forth. The math isn't working out exactly because, again, they've rounded these expected counts. But anyway, but that's how these residuals are computed. Right away, so what the reason I point this out to you is because I think looking at the residuals is useful because you can tell right away which categories had the largest difference, right? Yellow had the largest difference between what was expected and what was observed. Anyway, but let's write down our p-value, 0.0005. Okay, so we went to art of stat, and for count, we put in the chart at the top of the page. I'm not going to make you copy down that chart, but we put in the numbers in the chart. And for props, we put in the null hypothesis. And again, I'm not going to make you copy all that down again. But the p-value that we got out of this was 0.0005. So that's pretty small, right? 0.0005 is less than whatever level of significance we usually use, right? It's less than 0.05. It's also less than 0.01 or any of the other normal level of significances that we tend to use. So we definitely reject, right? I almost wrote definitely. We reject H null. Okay. We're rejecting the null hypothesis in favor of the alternative. So the evidence suggests, right, that at least one of the proportions is different than stated, right? There is sufficient evidence to conclude that at least one M&M color occurs with a different proportion than hypothesized in H null. Okay, so at least one of the colors is different. Part B, what do you think the residual measures? Well, we've talked about this, right? Which color had the largest residual? It was yellow. Comment on how the color distribution in our bag differs from the color distribution claimed by Mars. So we would say the residual measures the difference between what was expected and what was observed. The largest residual was for the yellow candies. And let's see if they'll still let us look at this. So looking at those residuals, yeah, yellow was the largest. I know it just grayed out, but we can still kind of see it. Yellow was the largest. Brown was also fairly elevated. So it looks like there are more brown and yellow candies and fewer of the other colors. Our bag had statistically significant or significantly more brown and yellow candies and fewer of the other colors. Okay, so that's how a goodness of fit test goes. Here's another one. You should pause the video, give this one a try on your own. I'm going to go ahead and give you my solution here. So it says, an urban economist wishes to determine whether the distribution of residents in the United States is the same today as it was in 2000. He randomly selects 1,500 households in the United States and finds the distribution in the table below. Test the claim that the distribution is different today than it was in 2000 at the 0.05 level of significance. Okay, well, the null hypothesis, if we call the Northeast group 1, Midwest group 2, South group 3, and West group 4, the null hypothesis is that the proportion of people who live in the Northeast is the same today as it was in 2000. So in other words, that P1 equals 0.190, and that P2 equals 0.229, and so forth. The alternative is that at least one proportion is different than stated in the null hypothesis. Let's go to art of stat to get our p-value. For counts, we're going to put in the observed row from our chart. And for props, we're going to put in the percent in 2000, okay, from the chart. And let's see what we get for our p-value. Okay, so we want a goodness of fit test. We'll do our own contingency table. We have 4 categories this time. We have Northeast, Midwest, South, and West. Okay, our counts are going to be the observed counts, 299 for the Northeast, 332 for the Midwest, 525 for the South, and 344 for the West. And for proportions, we have 19% in the Northeast, 22.9% in the Midwest, 35.6% in the South, and 22.5% in the West. Okay, then we can click on Submit. And we get a very large p-value here. We're not going to be rejecting the null hypothesis. If you look at the residuals, you might be surprised because you might say, well, wait, hang on a second. In the previous example, the largest residual was 10, and here the largest residual is 14. So how is it that we can't see a difference? Well, the reason is because our sample size is much larger, right? We've got 1,500 people in our sample size this time. And so, of course, the differences between what was observed and what was expected are going to be larger, but that's not an indication in this case. That's not, you would have to have much larger differences in order to say that that the distribution of where residents live in the United States is different. Okay, yeah, so our p-value 0.07 or 0.7174. 0.7174. So our decision here is 0.7174 is not less than 0.05 was our level of significance. It's not less than 0.05, so we do not reject H null. There is not sufficient evidence to conclude that the distribution of U.S. residents is different today than it was in 2000. Part B, what does the p-value measure in this scenario? Well, if we assume that the null hypothesis is true, and the null hypothesis in this case is that the distribution today is the same as it was in 2000, right? Okay, so if we assume H null is true, then there's a 71.74% chance 71.74% chance of obtaining the sample results that we obtained. Okay, that's a really high likelihood. So no reason to cast doubt on the null hypothesis, right? That's a really good chance. So we don't reject the null. Part C, according to the results of this study, has there been a statistically significant change in the distribution of U.S. residents since the year 2000? No. And we'll just leave it at that. Let's talk about homogeneity of proportions tests. So this is the last test that we'll talk about for comparing multiple proportions. What the homogeneity of proportions test does is it determines whether the proportion of subjects in various groups who have some characteristics are homogeneous, or in other words, the same. To run this test, we first have to arrange the data into a contingency table. So just to give you an example of what the homogeneity of proportions test looks like, this says Zocor is a drug that's meant to reduce the level of LDL cholesterol and increase the level of HDL cholesterol. Researchers were interested in determining what side effects are caused by Zocor, so they randomly divided patients into 3 groups. Group 1 received Zocor, Group 2 received a placebo, and Group 3 received cholestyramine, which is a cholesterol-lowering drug that's already available. Is the proportion of people who experience abdominal pain the same in each group? Well, the null hypothesis would be that it is, right? That the proportion of people in Group 1 is equal to the proportion of people in Group 2, which is equal to the proportion of people in Group 3, right? P1 equals P2 equals P3. The proportion of people who experience abdominal pain is the same in all 3 groups. And the alternative hypothesis, again, we're going to write this out in words because there are so many ways that the null hypothesis could fail to be true. It could be that P1 and P3 are the same, but P2 is different. Or maybe all 3 of them are different. Or maybe P2 and P3 are the same, but P1 is different. So we'll just say at least one proportion is different from the others. Okay, so that's what the null and alternative hypotheses will look like. To run the test, like we said, we first have to arrange the data into a contingency table like this. So we would set it up where we put, the different groups along the top, and then whether they experienced abdominal pain, right, along the first column. And of course, we're going to have row totals and column totals, right? And then a grand total, right? A table total. Just like we've seen with contingency tables before. Now, if we want to compute the sample proportion of people who have who fall in a particular place on this contingency table, the way we would do that, let's say, for example, that I wanted to know the proportion of people in the cholestyramine group who did not experience abdominal pain. This would be row 2, column 3, right? It's row 2, column 3. So what we would do is take the row 2 total and divide it by the table total and multiply that by the column 3 total divided by the table total. Now the reason for that is because if it is the case that the null hypothesis is true, then whether or not somebody experienced abdominal pain is independent of the medication that they took. This is something we'll talk about in more detail in a future section. But if they're independent, then we can use the multiplication rule for independent events, and we can say, okay, so the proportion of people in the cholestyramine group who do not experience abdominal pain is going to be the proportion of people who do not experience abdominal pain, that's row 2 total divided by table total, times the proportion of people in the cholestyramine group, that's column 3 total times the table total. So that's how we get those sample proportions. We're not going to be doing any of this by hand, by the way. I just thought I'd give you some of the reasoning that's going on behind the scenes. Of course, if we don't want the sample proportion, but instead we want the expected value, then we would multiply again by the table total, and we would just end up with this expression for the expected values. And this is what the calculator, this is what the app will be doing when it computes expected values for us. Those expected values all need to be bigger than 1, and 80% of them need to be bigger than 5 in order for us to run this test. Same conditions as for the goodness of fit. Okay, so here's what a chi-square test for homogeneity of proportions looks like, okay? The null hypothesis is going to be that all of the proportions are the same, and the alternative is going to be that at least one of them is different from the others. Step 2, gathering the sample proportions, right? This is optional, but if you wanted to, like, this is how you would compute those sample proportions. And then I'll show you how we compute the p-value in a second. If you want to know why it works, then you can follow this link and read that for yourself. But the p-value has the same meaning as usual, right? It's if we assume the null hypothesis is true, the p-value is the probability that we would obtain the information that we obtained in our sample. So let's just complete the Zocor example that we got started with. It says Zocor is a drug that's meant to lower LDL cholesterol and increase HDL cholesterol. And we want to know if people who take Zocor are more likely to experience abdominal pain. So these are the results. They've given us the results now. They didn't give us the totals, but that's okay. Is there evidence that the proportion of subjects in each group who experience abdominal pain is different? So we'll call the Zocor group Group 1, placebo Group 2, and cholestyramine Group 3. The null hypothesis is that P1 equals P2 equals P3. Okay. The alternative hypothesis is that at least one proportion is different from the others. And to get our p-value, we'll go to art of stat. Let's see what we need to enter into art of stat in order to run a homogeneity of proportions test. So once again, I'm not going to get data from the textbook. I want to do a contingency table. So they ask us for a row variable name and then the categories in that row, and then the same thing for the column. So in our row, the rows were whether or not somebody experienced abdominal pain. Whoops, ab pain. And the categories in our case were just yes or no, right? They either experienced abdominal pain or they did not. Put a comma between the different categories. And you can see over here it's filling in the contingency table as we go, right? The columns were medication taken. And the possibilities were Zocor, comma, why is it changing this? Zocor, comma, placebo, comma, and cholestyramine. Okay. And then once you have all those things filled out, then you can enter the counts into the contingency table. So for Zocor, there were 51. 51 for the placebo, 5 for cholestyramine, 16 participants who experienced abdominal pain. For participants who did not experience abdominal pain, it was 1,532, so the vast majority, right? 152 in the placebo group, and 163 in the cholestyramine group. Okay, so once you finish filling all of that stuff in, you get these really nice side-by-side bar charts so you can compare the different groups. You get this contingency table, this conditional distribution, all kinds of good stuff. What we're really here for, of course, is the p-value. Our p-value is small in this case. You also have options to do some other things over here. So the conditional distribution may not be super, helpful for us right now, but we might want to look at the expected counts, okay? So looking at the expected counts, again, we need to make sure that all of the cells here are at least 1, and 80% of them need to be at least 5. They're all bigger than 5, so we're good. The conditions are met. We also might want to look at the residuals. So we can click on residuals, and these residuals have the same interpretation as the residuals for the goodness of fit, right? This tells us how much of a difference we're seeing. Okay, so the residuals might be helpful to look at. So what we're seeing is that we observed 51 Zocor patients to have abdominal pain when we expected about 59 of them to experience abdominal pain. So we actually observed fewer Zocor patients with abdominal pain than what we expected. So this is great news for Zocor. If you look at cholestyramine, on the other hand, we observed 16 cholestyramine patients with abdominal pain when what we expected was only about 7 of them to experience abdominal pain. So that's bad news for cholestyramine. It means that cholestyramine is probably the cause of abdominal pain, whereas Zocor almost certainly is not. Okay, but what we're really here for is the p-value 0.0006. Okay, so as far as work to show, we went to Art of Stat, we entered the contingency table, and we got a p-value of 0.0006. That's very small. It's less than 0.05. So we reject the null. Since we're rejecting the null, that means there is sufficient evidence to conclude that the proportion of patients with abdominal pain is not the same in each medication group. Okay, that's really all the hypothesis test tells us. But again, you can look at the difference between the observed and expected counts, right? You can look at the residuals, and you can kind of get a feeling for what the situation is. And it looks like the group that experiences the most abdominal pain is the cholestyramine group, right? Zocor actually had a lower incidence of abdominal pain than was expected. So that's good news for Zocor. Okay. As discussed previously, an equivalent way to view the last example is in terms of independence, right? If there's no difference in the proportion of patients who experienced abdominal pain between medications, then the variables abdominal pain and medication are independent. If there is a difference, then whether a patient experienced abdominal pain depends on the medication that they took, right? This is why the test is called test of independence / homogeneity in the art of stat, right? That's the title of it. And it's because really when you're running a homogeneity of proportions test, what you're doing is you're running a test of independence. Now, despite these tests being equivalent, in order to interpret the results correctly, we need to be more careful than we have been about the way we state our hypotheses. That distinction will become clear to us when we consider a contingency table with more than 2 rows. But for now, we'll save that discussion for later. For now, let's just look at another homogeneity test. So you should pause the video, give this one a try. It says in a study of 1,358 randomly selected deaths of men aged 45 to 64, the victim's smoking habits, along with whether the individual died of cancer, are listed. Are the proportion of cancer deaths the same in each smoking category? If we call non-smokers group 1, mild smokers group 2, moderate smokers group 3, and chain smokers group 4. I'm not sure who named these categories, but if we go with that, the null hypothesis for a homogeneity of proportions test is that the proportion of people who died of cancer is the same in each of these groups. The alternative is that at least one proportion is different from the rest. Okay, we'll go to Art of Stat to get our p-value, and we'll enter the contingency table. Okay, and then we'll see what we get for the p-value. Okay, we don't want to use a textbook example. We want to use our own. Row variable will be whether they died of cancer. And the categories are going to be yes or no. The column variable is going to be smoking habits. And we had 4 categories there: non-smoker, mild smoker, moderate smoker, and chain smoker. And then we can put in the number of successes and failures. 55 for non-smokers, 52 for mild, 88 for moderate, and 135 for chain smokers. And then we have 305, 298, 225, and 200. So click out of the contingency table, and then the calculator will compute the results for you. We have a very small p-value here. It's so small that the calculator doesn't have enough space to store all the digits, right? So it's just saying the p-value is less than 0.0001, right? Okay, you can sit here and kind of stare at the side-by-side bar chart and get some ideas about what's going on here. I think it's helpful to look at the expected counts and compare the expected counts to what was observed. You can also show the residuals for that. Okay. And we are asked to do this as a follow-up on this. It says describe the relationship between smoking habits and cancer death. So what I'm seeing is that the expected number of cancer deaths was higher than what we observed for non-smokers. But for chain smokers, the observed counts were higher than what we expected. So for non-smokers, the observed counts were lower than expected, and for chain smokers, they were higher than expected. And in fact, you can see almost a perfect kind of linear correlation between those things, right? As we increase our smoking habits, we are increasing the number of cancer deaths, right? Okay, but let's write down our p-value and then we'll make that observation. That's not like an earth-shattering observation, right? but that's what the data seem to bear out in this case. Okay. Decision. I forgot to say our p-value is less than 0.0001. We would say 0.0001 is less than our level of significance, 0.01. So we reject H null. There is sufficient evidence to conclude that the proportion of cancer deaths is not the same in each smoking category. Right, and that's the conclusion of the hypothesis test. But to answer the follow-up question, describe the relationship between smoking habits and cancer deaths, we would say the more a person smokes, the more likely they are to die of cancer. And just to be clear, I'm not saying this because it's sort of common sense. I'm saying this because this is what the data indicate. When you look at the contingency table, when you compare the observed deaths versus the expected deaths, right? This is what we see in the data. Okay, we have covered a lot of ground. This has been a long lecture, and thank you for hanging in there if you're still with me. Let me just summarize real quick, okay? We've discussed in total 4 tests for proportions. We talked about the one sample proportion test from sections 3.1 to 3.3. And this is where, we're just testing a single proportion, p equals some number, and then we can run it two-tailed, left-tailed, or right-tailed. We talked about in this section the 2 sample proportion test, which is similar to the 1 sample proportion test, only instead of saying p equals some number, we're saying p1 equals p2, right? But again, we can run it two-tailed, left-tailed, or right-tailed. For comparing more than 2 proportions, we talked about the goodness of fit test and the homogeneity of proportions test. In the goodness of fit test, we have, in our null hypothesis, p1 equals some number, p2 equals some other number, and so forth. Whereas in the homogeneity of proportions test, we don't really care what the proportions are. We just want to know if they equal one another. At first glance, that might seem like the goodness of fit test is like a stronger test in some ways, but actually we'll see later on that the homogeneity of proportions test is really a powerful test. And we'll talk about that later. Note that the goodness of fit, okay, number 3 here, is a generalization of the 1 sample proportion test number 1, in the sense that we're saying, the proportions are equal to some number, right? So 3 is sort of an extension of 1, whereas the homogeneity of proportions test is a generalization of the 2 sample proportion test, right? So 4 is a generalization of 2, okay? In the sense that we don't care what the proportions are, we just want to know if they're equal to each other. Note that, as I've said, with the goodness of fit test, the difference between the goodness of fit and the homogeneity of proportions is that With the goodness of fit, we have exact values for each proportion, while with the homogeneity of proportions test, we don't. Note that a goodness of fit explores more than two proportions that come from one population, while a homogeneity of proportions test explores more than two proportions that come from more than one population. Okay, if we want to know whether the proportions of candy colors in a bag of M&Ms are equal, then we run a goodness of fit. But if we want to know whether the proportions of candy colors in one bag of M&Ms match the proportions of candy colors in another bag, then we would run a homogeneity of proportions test. So again, we'll consider this in more detail when we look at the connection between homogeneity and independence, which we will do in a future section. But for now, we'll practice with the information that we have here. Again, thank you for making it this far, and that'll do it for this lecture.